Welcome back to Explicit Tutorials. In today's video, we are going to talk about the remaining 4 laws of set. So let's kick off with the fourth law of set, which is the Morgan's law. The Morgan's law. Now, the Morgan's law states that when you have A intersect B, then the complement of A intersect B, it is equivalent to the complement of A union the complement of B. Or when you have A union B, then the complement, it is equivalent to the complement of A, intersect it with the complement of B. So we want to verify if this is very true. Mind you, the intersect changed to union and the union changed to intersect, but the complement sign came for both sets. So the Morgan's law is basically for comparing 2 sets. So let's verify if it is true. So let me first of all do A intersect B. If we have A intersect B, A intersect B are those elements that B has in common, which is this part. Now the complements of A intersect B are those elements that are in the universal set, but not in A intersect B. So these are the elements. Not just this part is also among the universal set. And not just these 2 parts, this other part is also among. So these are the elements that are in the universal set, but not in A intersect B. So the shaded region is this part. So let's compare it with A complements and B complements. First of all, A complements are those elements that are in the universal set but are not in A. These are the elements that are in the universal set but are not in A. So these are those elements. This region. This is our A prime. The element, these are A, these are B. The elements are in A that are in the universal set but not in A. What about our B complements? Our B complements are the elements in the universal set but not in B. These are the elements in the universal set that are not in B. Now, when you now add up this shaded region to this part, you find out that basically this part will be added to it, but these 2 parts are not even there. So when you add this shaded region with this shaded region, what you are going to get is this. So the Morgan's law has been proven to be very, very true and correct. What about the second, the Morgan's law? When you have A union B, adding A and B together, then the complement, it's basically the outer part. Or let me draw it. You have A, B. A union B are those elements in A, adding it up with the elements in B. Now, what will now be the complement of A union B? They are those elements that are in the universal set, but not in A union B. So it's actually this region. So let me use another way of shading. So it's actually this region. So let's compare it with A intersect, A complement intersect B complement. So let's compare. Now, what will be our A complement? Our A complement is already this. These are A complements. Then these are our B complements. Now, if these are B complements and these are A complements, when you intersect them, what do they have in common? They have this part in common. They do not have this part in common. Neither do they have this part in common. So when you intersect these 2 things, what you get is this shaded region. So the Morgan's law has been proven to be very, very correct. Now, for the independent law, it's comparing a set with its set. Now, when you have a set A and you add it up with itself, you will get the same set. There's no need for you to stress yourself and prove it. It's something you can easily just see and know. Now, when you have a set, you intersect it with the set, you get A. When you have a set A and you add it up with its set, you will still get the same A. So this independent law is already verified to be very, very true. What about the complement law? The complement law. The complement law is still comparing a set and itself, but you are not just comparing it with itself. You are comparing the set with its complement. So let's compare the set A and its complement. So first of all, we want to look for A intersect A prime. So we want to verify if A intersect A prime is actually an empty set. No need for me to compare with other sets. I can just use only this kind of figure. So what would be A? This is A. And this is A prime. This is A and this is A prime. The elements that are in the universal set but not in A. So what do these two elements have in common? They have nothing in common. So the intersection of these two elements is an empty set. That's why we have phi. So this has been verified to be true. What about when you add these two sets together? When you add these two sets together, you get back the universal set. That is why they said A union A prime is the universal set. So this is verified to be true. So what about the complement of set A? The complement of set A. Okay, before I do this, let me do this. Now, what is the difference between A and A prime? It's those elements that are in A, but not in A prime. What are those elements that are in A, but not here? The elements that are here, but not here, is actually those elements that are still here. So, it's very true that the different sets of A and A prime is A. The elements that are in A, but not in this part, is still the same set A. So this has been verified to be true. Now let's do for the symmetric difference. What is asymmetric? A prime. The elements that are here, but not here, is still this. While the elements that are here, but not here, is this part. Now when you add them together, you will get back the universal set. So this has been verified to be true. Now let's compare with the complements of A. Now this is already our A complement. This is already our A complement. What will be the complement of this? What will be the complement of this? The complements of this are those elements that are in the universal set but not in this shaded region. So what are those elements that are in this place but not in this shaded region? It includes these elements in this smaller circle. That is why the complement of a set is the set A. The complement of the complement of set A is actually the complement of A. While the complement of the complement of the complement of the complement of A is A, and so on. So that's for the sixth law. Let's move over to the last law of set. Okay, welcome back. So let's go over to the last law of set. Whew. This is the identity law. In the identity law, we are comparing a single set, that is a set A. I didn't mean a singleton set. A set with either its empty set or we are comparing it with the union set. That's what the identity law is all about. So some of them you necessarily do not need, you don't have to use Venn diagram to prove them. You just know. Now, what we are looking for A intersect phi. We want to see if it's phi. Now, what do the sets A have in common with an empty set? They still do not have anything in common. So this is an empty set. So that part has been verified. Now, you have a set A and you add it up with nothing. You will still get the same set A. So it means that the union of a set and an empty set is the set. Now, what about the symmetric difference of A and the empty set? The difference between A and the empty set are those elements that are in A but not in the empty set. The elements that are A that are not in the empty set is actually still those elements in A. This has been verified. So what about those elements that are in the empty set but not in A? There's no elements here. This one is just, should I use the word undefined? The elements that are not here, that are in A but not here, is still phi. There's no set like that. There's no element that is here that is not here. So it's really, should I use the word undefined for this one? So this is verified. So what about A minus U? What are those elements that are in A but not in the universal set? There are no elements that are in A because the universal set has every other element. So there is basically no element in A that is not in the universal set. So this is verified. Now when you intersect A and the union set, what are those elements that A and the universal set have in common? It is still those sets that are in A. So this one is verified. So most of the independent laws do not necessarily need your Venn diagram. It's something you can just picture easily. What about when you add up the set A and the universal set? Whatever you get will still give you the universal set because you actually made no difference. What about when you find the symmetric difference of the set A and the universal set? Alright, the symmetric difference of these two things are those elements in A first of all that are not in the universal set. What are those elements that are in A but not in universal set? Is actually an empty set. This is it. Adding it up with those elements that are in the universal set but not in A, which is your complement set. The element that are in the universal set but not in A is actually the complement of A. So adding empty sets with your A prime, I think we've done something like that. We still give you your A prime. Okay, A union phi is A. So phi union A prime will still give you A. So this is also verified. Which other one? So let's verify this. What if you have a symmetric difference phi? What are the elements that are in A that are not in the empty set? It's actually A. Then you're adding it up with those elements that are in the empty set but not in A. It's still your phi. A union phi will give you A. So this has been verified. So that will be all for the 7 laws of sets. In our next video, we'll be solving some problems using these laws. Alternatively, you can use your Venn diagram, but we'll be solving them using these laws of sets. So thanks for watching. Do not forget to like and subscribe to this YouTube channel. Turn on your notification, and if you have any issues, state in the comment section. I will do a video for you, a very explanatory video for you. Thanks for watching.